Okay, so we will continue with this module on the method of moments and look at the next section, which is applying this method of moments to surface integral equations. Okay. So, again we will do a little bit of revision. If you remember, this was the two volume problem. I had some scattering object, so I had indicated like this, and this was surrounded in a bigger region. I had called this boundary S infinity, this was S, and there was some current source over here J. This was my volume 1, this was my volume 2, okay. And this volume 2 is some object, okay, which I know. So, these were the two equations that we had got, right. Everyone remembers these equations. So, what just to refresh your memory, what changed to produce either this or this, the first or the second equation? Position of r dash, yeah, but why do I get two different right hand sides? Because of the location of the delta function. If the delta function was not in the region of integration, then I got a 0, which happened when r prime was in V2, right, and when r prime was in V1, then the delta function acted with phi 1 and I got phi 1 r prime, right. Similarly for region 2, again just to refresh your memory, why is there a minus sign in the first equation and a plus sign in the second equation? N cap, right. I had fixed the direction of n hat to be this way. So, for the outward the surface, the outward normal being fixed this way for V1 and V2, there is a minus sign difference. Any other difference that we notice? The incident field. There is an incident field only in region 1, in V1, right, that is why it is there here, but in the second equation it is not there. Okay, so, everyone remembers this. We had even given names to these equations. So, the first equation on both sides, what did we call it? Huygens principle. Okay. Similarly for here, and this one we called extinction theorem. Right, so this is just a revision for you. And now the after we introduced these equations, what did we do? We went and had a long discussion on how do we calculate G's, okay, and we also looked at integration, because you can see there is an integration here, we will have to worry about integration. Okay, so that was the general setup. Moving further, one thing we realized was that grad phi 1 and phi 1, these are not being evaluated anywhere in space, they are only being evaluated on the this is a line integral or a contour integral. So, these were only being evaluated on the surface S, and then what relation did we use to say that phi 1 and phi 2 should be the same? So, there is a phi 1 here and there is a phi 2 here. The two on the boundary are the same because continuity of tangential equations, right. So, continuity of tangential E field gave me phi 1 equal to phi 2, and continuity of H tangential gave me grad phi dot n hat is the same on both sides. Okay. So, recognizing that, I am writing a new symbol grad phi dot n hat, that is the same in both equations, and phi 1 phi, right. So, what I have done is I have chosen only the extinction theorem, right. So, now in these equations, what is known? If I ask you, looking at these equations, what all is known? Let us start from the left. Do I know G1? Yes, it is Green's function for medium for volume 1, I know it. G1 is known, G2 therefore is also known. Do I know the phi's? I do not know the phi's, that is what I want to find out, but I know the right hand side, this guy, I know the incident field, phi I is known. And what is unknown now, which I want to solve for? Phi is definitely unknown. Can we make the other unknown a little bit more precise? Grad phi dot n hat, right, because I mean n hat is known, but what is easier, to solve for a scalar or a vector? Scalar, right. So, if I know n hat, instead of trying to find out grad phi, which is a vector, may as well make the new unknown grad phi dot n hat, right. So, grad phi dot n hat, right. So, these are my two unknowns. So, I have two sets of equations in two variables, and the goal is to solve these two equations. Okay. So now let's use our method of moments approach to solve these problems. Okay. Now one thing that you will notice is in these equations, what is the variable of integration? Is it r or r prime? R, unprimed coordinates, right? That's indicated over here. So it's unprimed. Okay, that's important. So in this equation, there is one thing that is yet not been specified, and that is staring at us in the face, which is I didn't say anything about r prime, right? So r prime, unless I specify r prime, I can't actually evaluate this first or second integral. Because where is r prime? All I have said is, all that extinction theorem says is r prime must belong to V2 and r prime must belong to V1 in the second part, right? So let's look at this. Let's draw this again. So for the first equation, where can first equation says r prime must belong to V2, right? So this is where r prime should be, right, for equation 1, and this is where r prime should be for equation 2. Okay, it's a very common mistake is to forget about this thing. If you forget about this, if you put r prime in the wrong place, then the right hand side will change, right? So these are the two constraints that have to be kept in mind. But other than that, r prime is it's in my hands. Okay. So now the question is, okay, fine, r prime must belong to V2 in the first case and V1 in the next case, but where exactly should I put them? I want to solve this by something like method of moments, and we'll take the simplest kind of method of moments. What is the simplest kind? Pulse basis delta testing. We'll keep this as the prototype. All right. So this having been specified, now for the testing location, I have to, testing location is corresponding to where I choose my r prime. So where can I choose my r prime? Okay, let's take one step back. Okay, let's start with the basis functions. Okay, we'll come to testing next. Let's start with the basis functions. So what are my unknown functions are phi and grad phi dot n hat. So for grad phi dot n hat, I can say that this is now my unknown function, which I will write in terms of a known basis. Known basis, I can, let me call the pulse basis as P n of r. Okay. So coefficient I can write as a n P n of r, n is equal to 1 to n. Okay. Similarly, for the other variable phi r, I can write this as in terms of n is equal to 1 to n, some new variable b n times the same basis function p n. Okay. So what have I done? I've chopped up this into n segments. For each segment, I have assumed one pulse with a coefficient that is going to be determined. Okay. So the unknowns, so the phi's I have made them into bn's, and the grad phi dot n hat I have made them into an's. Okay. So the pulse basis, the basis function is done, clear. Next comes the location of the testing function, the testing point. Is a delta testing, so I just have to pick a point. Where should I place my testing function? So what should we do? I mean, it's not very complicated. What would you do? So look at what the constraint, r prime for the first equation can be anywhere in V2, right? So supposing, let's take one case over here, this is my V2, okay, and there are various n segments over here like this, and it's up to me where I choose these points. Can I choose these? So how many segments are there? 1, 2, 3, 4, 5, 6, 7 segments. So how many points should I test at? 7 points, right? The first equation will give me 7 and the next will also give me another 7. So, I will get 14, I will get all my 14 variables. There are 14 variables in this case, right. Each segment has a AN and a BN that I need to find out, right. So, I could choose these 7 points anywhere here, I could choose these points like this, right, for this is for equation 1. Can I choose my points like this? Yes, technically there is nothing wrong with this. Why? Because if I put these points in over here, one by one if I go through them, how many equations will I get? I will get 7 equations in how many variables? The first equation, how many variables are in it? 14 variables. So, I got 7 equations because I tested at 7 different points, I got, and there are 14 variables. So, I got 14 variables, 7 equations. So, then, but I have used only half the information in the problem. The other half is equation 2. Equation 2, how many times should I test? Again 7 times, then I will get 14 equations in 14 variables. So, where can I choose these points? They have to belong to volume 1. So, I could choose some points like this, right. So, 1, 2, 3, 4, 5, 6, 7, 7 points have been chosen. So, that gives me, when I test the second equation with these 7 points, I will get the remaining 7 equations and the same 14 variables, right, because grad phi is appearing in both places, phi is appearing in both equations, right. So, I am going to get 14 equations in 14 variables, I can solve it, I will get my answer. Is there any problem with this approach? No, there is no problem. Only thing is that the location of these testing points seems a little arbitrary, right, I just pick them anywhere, right. So, if I pick these points like this arbitrarily in V1 and V2, then I mean theoretically it is correct, and doing so is called the extended boundary condition method. Extended boundary condition method. Why extended? Because it is away from the boundary. So, extended boundary condition method. Okay. But as it turns out, so I am not going to derive this, but I will just give you information. If you pick these points at random like this away from the boundary, the error in the solution is high. Okay. So, what might be another way of picking it? I let these points go very close to the surface. If you think back at the first integral equation that I did, that wire, where did I pick my testing points? Middle of each segment. Can I do middle of each segment here? I get 1 no. Anyone saying yes? I mean a segment like this. Can I pick my r prime here? It is known. So, if the boundary is known to me, right, n hat is known to me. So, I can pick my location anywhere as long as I am obeying these constraints. N hat is given to me, I know the boundary. Can I pick my points can I move this guy over here? I can move it as long as it is not, even touching the boundary is okay. I mean the boundary is a sort of a peculiar object, right, the boundary belongs to both V1 and V2. So, as long as I do not go across the boundary, I am not violating the condition of extinction theorem, right. So, what I can do is, let us just take one zoomed in segment over here. ANs, okay. So, the question is what are ANs in this picture? So, let us take one if you look at, I have n segments over here. So, AN represents on this boundary, there are n segments. So, A1 for example will be the amplitude of the first pulse basis function, A2 will be the amplitude of the second pulse function, that corresponds to grad phi dot n hat. Grad phi dot n hat is a scalar. It is a scalar function that varies on this boundary, right. I am expressing this function by saying that it is made up of 7 pulses. So, A1 is the amplitude of the first pulse. So, it's a little bit like this. I have some function. Let us say that this is what grad phi dot n hat looks like. Okay. And the starting and ending point is obviously the same because I am going on a circle. Okay. So, technically I should not draw it like this. So, let us say something like this. Okay. So, this point and this point is the same. So what I am doing is I am chopping it up like this, right. That's my grad phi, this is my grad phi dot n hat is the continuous curve. I am saying I will approximate it by something like this, these pulses. Okay. As I make more and more pulses, I can approximate it better and better, right. This is the old stuff, we have already seen this. Okay. So, now coming back to this one segment over here, the first point over here, I can move it in a limit very close to the midpoint of this segment, and the testing point from the second equation, I can move it very close to the middle of the segment. Again, I can take a limit. Okay. So, I can think of this being the surface S and one imaginary surface, let me use green over here, drawn like this, and an imaginary surface drawn like this over here. Okay. So, the inside one I can call S minus and the outside one I can call S plus, right. So, the plus and minus is to make sure that we obey our the conditions of extinction theorem. Okay. As long as I am in S minus, this condition is valid because it's in V2, right. So, what I am going to do is, if I choose these points basically to be the midpoints of the segments, then I have a very clear unambiguous way of specifying how to solve this problem, right. Pick these basis functions 1 and 2, pick the testing points to be the midpoints of each of these segments, just like how we had done in the first example on integral equations, right. So, that's the strategy that we will use, and when we solve it like that, it's called the, so it's simply called the boundary integral method. Okay. So, this is would be called the boundary integral method. Okay. So, S minus is for r prime belonging to V2 and S plus is for r prime belonging to V1. That is what we have done. Okay. Now, why I need to define this S plus and S minus will become clear as I go. I may as well just have said pick the midpoint, why to tell you about S plus and S minus. Okay. So, that will become clear as we go along. What else is there in this equation to solve in the method of moments? What will happen? I will substitute this guy and this guy, phi and grad phi dot n hat into this equation, right. So, what kind of terms do I have to evaluate? I will have to evaluate the integral of g1 over some segment and the integral of grad g1 dot n hat. These are the two functions whose integral I have to evaluate, right, when we do the method of moments. We looked at the AMN, the matrix coefficient AMN in terms of the operator yesterday in the language of method of moments. That's the coupling coefficient, so to speak, that I have to evaluate. Okay. So, so these are the things that I have to worry about. Okay. So, let's take a segment, let's call it segment I. I'll have to evaluate G1 RR prime dr, okay, or let's just call it dl because it may be curved, and I have to evaluate grad G1 RR prime n hat dl. That's what I have to evaluate. A segment means a segment like this, and sum over all such segments. I have broken up the whole thing into several segments. I have to evaluate this integral over each segment.
Basically, that Bn of r is causing that segment.
Yes. So, because my basis functions are pulse functions, so this pulse function is non-zero only over one segment, right. So, when I go to evaluate the integral, I have to do this integration sort of for each segment one by one. Okay. That is because I am using subdomain basis functions. So, they are non-zero only in one part of the segment. Is that clear? Okay. So, these integrals are the ones that I have to evaluate, this and this, for both G1 and G2. Okay. Do we have we learned anything already which helps us to evaluate these integrals? Numerical integration, we have already seen one module on numerical integration, and the reason why numerical integration is necessary is because these functions, Hankel functions and so on, they are often not analytically integrable. So, I need to evaluate these numerically. So, I will use things like quadrature rules to evaluate this, right. Quadrature, remember what was the advantage? I do not need to know anything about the function except its values at some points. Multiplied by pre-computed weights, I get the integral. So, that is going to be a strategy.